This is going to be chapter 11, sequences and series tests. So let's first start off by defining what a sequence is. So if you think about a sequence is just some sort of list of numbers that maybe might follow some sort of pattern. So if you think of 1, 2, 3, and 4, this is a sequence. You can think of 2, 4, 6, 8 is another sequence. So we have this sequence of numbers. So in general, we would write them as A1, A2, A3, A4, similar to what you've seen in a pre-calculus class. Now, usually we have some notations for sequences. So if you want to be able to think about sequences with some sort of notation, we typically write, if you want to write the list like this, A1, A2, A3, continues on all the way to AN, well, we usually would write them like this, with curly braces and then AN. Sometimes you might see books do them like this, A sub n, or n goes from 1 to maybe infinity. So here we're not talking about a finite sequence. Maybe I shouldn't write this, but this basically means that you're going from A1 and then continuing AN and then continuing basically forever. So so here is just some notation that you might be able to see. This is just basically whenever you see these curly braces with A sub n, that just represents a sequence of numbers. So let me give you an example. So given this one, A sub n plus 1 is equal to negative 1 to the n, A sub n over 2, and A1 is equal to 3. Find the first 3 terms. So let's say you have something that looks like that. Okay, so basically what this says, when you see the word, the thing A1, this means that this is going to be the first term. So this is the first number in our sequence, the first term. Okay, so A1 is going to be equal to 3. That's just what's given to us. Now, how are we going to figure out the second term? Well, all we have to do is look at our general equation right here. So what we're going to plug in, 1 in here. Okay, so I'm going to plug in A1 plus 1 for n is equal to negative 1 to the power of 1, A1 divided by 2. Okay, so what this is going to give me, this is just going to give me A2. Okay, this is equal to negative 1 to the power of 1. A1 in this case is equal to 3 divided by 2. This is just going to give me negative 1, and this is going to give me negative 3 over 2. Okay, so that's that answer. Okay, now how am I going to find A3? Well, if this was by just plugging in n equals 1, then the next thing that I got to plug in is n equals 2. Okay, so I'm going to plug in 2. Okay, plus 1 is going to be equal to negative 1 squared A2 divided by 2. So this tells me that A3 is going to be equal to negative 1 squared, just gives me 1, positive 1. A2, we just figured out what that was. That was just equal to negative 3 halves divided by 2. And this is going to give me a negative 3/4. Okay. All right, and now let's try to figure out what happens when n equals 3. Gonna plug in 3 in there. A3 plus 1 is equal to negative 1 to the third power, A3 divided by 2. So negative 1 to the third power is going to give me a positive 1. Okay, so it's going to give me A4. Oh no, a negative 1. A3 gives me negative 3/4. And then divided by 2. That's going to give me positive 3 over 8. Okay, so you can continue doing these problems. Sometimes they might give it to you like that. Sometimes you might see problems that look like this. AN is equal to, I don't know, 2n plus 1. And then here you would just plug in n equals 1 and then just plug them in and then you will get it. So if you want to figure out what A1 is, you would just have 2 times 1 plus 1. That's just going to give me 3. If you want to plug in 2, then you're going to have 2 times 2 plus 1. This gives me 4 plus 1 gives me 5. Okay, A3, same thing, 2 times 3 plus 1, that's going to give me 7. And notice that all of these numbers start becoming a sequence of numbers. Okay, So this is what a sequence basically is. So here is a formula for the sequence. Someone has come up with this formula. Now here is the sequence itself. Okay. Now, what usually we want to figure out is if we start looking and listing these numbers 3, 5, 7. Notice that if as they get bigger and bigger, notice that, or as n increases, as n goes to infinity, this guy just gets completely big. Okay, but there's going to be other sequences. So, for example, 1, 1/2, 1/4 continues on. Whereas n goes to infinity, this precisely is not going to get bigger because you can see that the numbers get smaller and smaller. Okay, so what we're going to try to do with these type, and especially in this chapter, is do these sequences tend to converge or not? Okay, so what we're going to say is that a sequence, okay, a sub n has a limit L, and we write limit as n goes to infinity of a sub n equals L. Okay, so if a sub n is close to L as n goes to infinity. Now, we've been using this notation of limits with regular functions. So now it seems really weird that we're now doing sequences, because sequences, I mean, you can say per se is kind of like a function as well. So we're also going to say this additional statement, in which most of you guys have already known. If we take the limit as n goes to infinity of a sub n, and this thing exists, then what we're going to call it convergent. So it converges to something, okay? Otherwise, we're going to call it diverges. So if it's anything else, like infinity, positive infinity, negative infinity, or it doesn't exist, it's just going to diverge, okay? So let's do an example. Does a sub n equal n over n plus 1 converge? Okay, so what is it? Okay, so does it converge, yes or no? Okay, well, one way to do it is just by taking the limit of this thing. Okay, so one thing that you can do is you can plug in numbers and you can list out all the numbers that you can look at, but sometimes it's not easy to figure out. So one way to do it is just taking the limit. So I'm going to take the limit as n goes to infinity of a sub n. Okay, so that what I'm going to have is the limit as n goes to infinity of n over n plus 1. Okay, and now what I'm going to do is I'm going to go ahead and try to figure out what this is. Now, the question is, can I use L'Hopital's rule on a sequence of numbers? That's kind of weird. But actually you can, and I'll show you a couple of things that you can do with sequences. So I'm going to use L'Hopital's rule. So I'm going to have the limit as n goes to infinity, because you can see if I plug in infinity, you basically get infinity over infinity, which is some no-no. So the top part is going to be a 1, the bottom part is going to be a 1, so the limit is just going to be 1. Because it is equal to 1, you can say that this particular sequence converges. Okay? So what exactly can you do, and what exactly is permissible? Well, do these sequences tend to follow the same thing as what functions would do? So this is basically what is permissible. Ta-da! Okay, so take a moment to kind of write down the green part and the blue part. So it's a lot of stuff, but a lot of it is things that you probably have seen. So for example, the first one says that if you take the limit as n goes to infinity of 1 over n to the power of r, so as long as r is positive, this is just going to be equal to 0. And you can imagine it because 1 over infinity is just basically 0. The second thing is that if you take the limit of the absolute value of a sequence and it equals 0, then the limit of the regular sequence is going to also be equal to 0. Okay. The third one says that if the limit as n goes to infinity of a sub n is equal to something, is equal to some limit, and the function f is continuous at L, then if all I can do is just basically take the limit as f of a sub n, plug that into the inside, that equals L, so the answer is f of L. So basically, if you know the function of something, and I apply a function to it, then it's just going to be the function, and then the limit in the inside. This one says that if the function, if the limit as n goes to infinity of some function is equal to the limit, and f of n is equal to a sub n, then n is a, and when n is an integer, then the limit of a sub n equals L. Okay, so this is basically saying that I can basically say I can make functions the same as sequences. Okay, so basically I can apply L'Hopital's rule. I can apply anything that I want. If I can do it with a regular function, then I can do it with a regular sequence. Okay, and then in blue over here, we just have some limit properties. So basically with sequences, you can, if you take the limit of two different sequences, it's just the limit of each sequence individually. That should be a minus right there. The limit of the product of two sequences is just the limit of the products individually. The limits of both of the sequences is just going to be the division between the limits of each respective sequence. If I have the limit of a sub n to some power, I can just take the limit of the inside and put the power on the outside, as long as the power itself is greater than 0 and a sub n is greater than 0 as well. And also the amazing squeeze theorem, which basically means that if you have a function that you can squeeze between two different other functions, then basically, and if these two limits exist to some limit, then that means the limit of the inside is also going to exist. So this has already been proven to you. You don't need to prove it anymore, but this is just what we're going to be using. So the way that we evaluated limits with functions is going to be able to, we're going to be able to do the same thing with the sequences. So in the next video, we're going to do some problems with using these theorems and properties.